Hello everyone, welcome back. Let us continue our discussion on reinforced concrete design. We are in week 5 and this is our second lecture. So today we are going to learn column design that we have started last week. So column design, and this week we have already discussed the first part of it. That means the column is under axial compression and uniaxial bending, right? And we also discussed different cases that may appear, and out of that we have derived the expression for case 2. Today we are going to study case 4. That means we have xu less than capital D. That means the neutral axis is within the cross section. So for this condition, let us first draw the stress strain profile and let us consider the same cross section. So we have B, the width of this cross section, and we have D, capital D, the depth of the cross section. Now we have this P force is acting at a distance, say E, and we have neutral axis here. Now, this neutral axis is at a depth of xu, which is equal to K times capital D. The extreme fiber in compression will have 0.0035 strain, and then we have this stress in steel, which is epsilon S. So at the ith layer of the steel, we can have a strain of epsilon I, and this ith layer is at a distance of yi from the centroidal axis. Now we'll have the stress profile with 0 at the neutral axis, then we have a parabolic part, and then we have a rectangular part, and for that stress is 0.446 FCK. So at this level, if we mark the strain, this is 0.002, and this is the compressive force, and this is the tensile force, say TU. Now, the distance up to which we have rectangular stress block, that is 3/7 XU, and remaining part is 4/7 XE. And the location of this force, compressive force, from the extreme compressive fiber is 0.416 XE. So now we have marked all of them, and then let us derive the sectional capacity. For that, again, area of the stress block A is C1 times FCK times D, where C1, if you recall earlier, we derived this 0.36 K. And C2 for this case is 0.416. What is C2? C2 times D is basically this location of the resultant force. Now, from these information, we can find out what is the ultimate axial capacity. For that, PU will have contribution from concrete, so that is PUC plus PUS. Now for the concrete, we have already identified the area of the stress block, that is 0.36 FCK times KD times B is the total force, right? So this area of the stress block we have already identified. Even during the derivation for beam bending, we have done this. So the first part is done. For the steel, we have n layers. So I ranging from 1 to n. ASI is the area of the steel in the ith layer times the stress, that is FSI minus FCI. Now, we know what is ASI. This is PI times B times D divided by 100. So we can modify this expression. We have here PI times B times D divided by 100. So that is the total capacity of the section for axial compression, right? So we normally write this in a different form. We'll come to this point. So PU by FCK BD is equal to 0.36K plus summation I equal to 1 to n. We have PI divided by 100 times FCK times FSI minus FCI. So now we have this axial capacity of the section derived. Remember the condition for XU less than. The next task is to find out the moment capacity. So for moment capacity, we have MU is equal to again contribution from concrete plus contribution from steel. Now from concrete we have 0.36 FCK times K times BD, force multiplied by the lever arm, which is 0.5D minus 0.416 XU, which is K times D. So let us see the stress block. So the location of this PUC is identified from this extreme compression fiber, so we can find out easily the lever arm, right? Plus we have steel, so every layer will offer a moment, so that we have to find out. For that we have ASI times FSI minus FCI times the location, which is YI. So if we have the ith layer, you can see here, so location we have already identified, so we can find out. So ultimately MU by FCK BD square is equal to C1 times 0.5 minus C2 plus we have summation I equal to 1 to n PI divided by 100 FCK times FSI minus FCI times YI divided by D. So now we have the moment capacity also for the section, and these are the two expressions, this one and this one we see in Indian Standard Code. So today we have derived those expressions for a section where XU is less than capital T, right? Now we can easily evaluate the sectional capacity, provided only one information we have to figure out, that is this location of the neutral axis. And as I told earlier that this is done iteratively, so we'll start with some assumption and then iteratively we'll solve the location. The moment we know the location of the neutral axis, that is k, we can solve the complete problem because we know the axial capacity as well as moment capacity. So the main task remaining is determination of epsilon I, because that will tell us the stress component FSI and FCI, right? So epsilon I will come from the strain diagram. We already have this linear strain diagram, so we know the locations of every layer of steel, and then we can easily find out that, and the expression is 0.0035 divided by XU times XU minus d by 2 plus yi. This is again very simple. It comes from the strain diagram here, and from that diagram we know the location of every layer of steel and we can find out respective strain. Now once we know strain, our next task is determine FSI and FCI. Out of that, FSI again we have discussed in detail in the previous lecture. So accordingly, depending upon the type of steel, we can easily find out the stress value in the ith layer of steel. If this epsilon I for that particular layer is more than the yielding strain, then we will select one value. Otherwise, we have to select the value from the stress strain curve. So that is easy. For FCI, we have 0.446 FCK times twice AI divided by XU minus 3D by 7 minus AI divided by XU minus 3D by 7 whole square. This is for epsilon I less than 0.002 and it will be 0.446 FCK for epsilon I greater than equal to 0.002. Again, for stress, you see we have initially a parabolic block. So if it is somewhere here, obviously we have to find out this value. Okay. For that, again, we have to solve the equation of parabola. This is very simple. You can easily do it. And if it is more than this value, so it is going to offer a constant stress, and that you can see. So what is AI? AI is equal to XU minus d by 2 plus YY. So this is actually AI. Okay, so now we have derived the expression for PU and MU for sections having neutral axis at XU, right? But we have to first find out the location of the neutral axis, and accordingly we have to see the expression for PU and MU. Now there are different modes of failure in column. So we can have compression failure, we can have tension failure, and we can have also balanced failure. They all depend upon the stress distribution and the extreme stresses. So when we'll solve the problem, we'll explain this. But these are the three different failures that may occur in column. So Now the next is we'll solve some example for column design, but column design, you can do it in two different ways. One is analytical method. That means the expressions, the equations we have derived for PU and MU. There is another approach. Recall, we derived this expression for mu by FCK BD square and also PU by FCK BD. So there can be an interaction diagram. So interaction diagram based design. We'll go through this. We'll see what is the interaction diagram. But for the beginners, we normally do not prefer to go by this interaction diagram. We always prefer analytical method because then you will draw the cross section, you will draw the strain profile, stress profile, and use the equations to derive the sectional capacity. And in fact, I will recommend you go by analytical methods and not the interaction diagram for the moment. But in the design office, we always prefer to have this interaction diagrams, and that we can directly use to design the column. Okay. So these are the two different approaches. As I said, we will prefer to use the equations that we have derived. We'll identify the different failure modes and accordingly we will design the column. But before we close today's lecture so that you can carry it forward, let us identify the design steps. So analytical method, steps. So step 1, assume location of NA. So we start with at the edge, that is K is equal to 1. So let us start with this assumption. So next what we do, we determine FSI and FCI corresponding to epsilon I. Then third stage, before that again we also derive or evaluate in the second step, evaluate PU, we call it 1 because we are in step 1. So using this information we find out PU1. Next is if PU is less than PU1, then actual XU is less than D, and if it is greater than PU1, then actual XU is greater than D. In the next step, what we do, we go for second trial. So we select a new value of XU and then calculate C1 and C2. Once we have it, then finally we again find out PU2 and then we check the convergence. Repeat this same procedure, check the convergence. Once the values are converged, then we have the converged location of neutral axis. Then for that, we again finalize epsilon I FSI and FCI. And the moment we do that, using these values, we can find out PU and MU. So that is the procedure we are going to follow when we design a column using analytical method. The only point to be noted here is that we have to solve this location of the neutral axis iteratively, and then at every step we have to find out the strains at different levels, and we will use stress strain curve to find out the stresses, and then once we finalize the converged location of the neutral axis, we can find out PU and MU. Okay. So with that, let us stop here. In the next class, we will solve some example and we'll see how we can design a column under uniaxial compression, axial compression and uniaxial bending. Please go through this derivations, and if you have any doubt, do let us know through emails, and then we will clear your doubts. Thank you very much.